Day 86, Notes on Water Molecules. We're looking at the structure of molecules here and how they join together. And tomorrow we'll be looking at the chemical reactions with water. But right now with the notes. What is water? Water is a compound made of 2 hydrogen atoms and 1 oxygen atom. And that's how we get the formula H2O. The little 2 refers to 2 hydrogens, and then we just have a plain old O, meaning 1 oxygen, and those are all bound together. Here we have some diagrams of water molecules, and they always form this certain shape. It's sometimes likened to a Mickey Mouse head with the 2 ears and the face. It always has this angle to it. And the hydrogen atoms are the small ones here on the side. They have a slightly positive charge because the electrons that go around it spend a little more time around the oxygens than around the hydrogens. But the electrons do a figure 8, so to speak, around the hydrogen and the oxygen, and that figure 8 holds these 2 atoms together. And the electron spends a little bit more time around the oxygen than the hydrogen. And so that gives the hydrogen a slightly positive charge. We have that written on both sides. And since the electrons spend more time around the oxygen, it has a slightly negative charge. And these different charges here allow one molecule to attract another molecule. For instance, this positive charge here would be attracted towards this negative charge down here, and that would bring these 2 molecules together. They wouldn't firmly bond together, but they would attract with a little bit of strength to it. They would still stay separate molecules, but they'd kind of tag along with each other. So what I want you to do next is to cut out these molecules, all 5 of them, and line them up in a line so that the 2 positive hydrogens of one molecule are close to the 2 oxygens of other atoms. And on the next page, I have a picture of basically what I want you to do. And here I have actually cut out the molecules from the previous page. So I have this negative charge here. I'll line this up here. And that negative right here is going to attract a positive of another molecule. So they'll kind of line up like that. And then we'll get another molecule, and this positive will attract the negative of another molecule. And then these positives here will attract the negative of another molecule. And so we end up with this long line. You may not be able to get all 5 written down or glued down here, but we can have it bend a little bit. So all of these molecules of water are attracted to each other, and they kind of stick together. Not real firmly. They can break and join up with other molecules all the time. But momentarily, at least, these will make a long string like spaghetti noodles. And they will flow over each other. And that allows water to flow from a glass to a pipe or whatever. Would you please cut those 5 and then glue them in a line sort of like this, where the positives of one line up with the negatives of another. Next activity. This is about surface tension. Surface tension is caused because water molecules attract one another in strings and large droplets can form. Because the water molecules are attracting each other, they can form these big piles that we see as drops. Water can pile up on a coin in a huge drop. Activity number 1, how strong is water? The equipment will be found in the middle island. You'll have pennies and paper towels are in the dispensers on the wall. You're going to have beakers, not 10 milliliter. These are going to be various sizes. Take whatever is available. You don't need a lot of water in them. Just an inch will be plenty. The pipette is like a medicine dropper. So you'll suck up some of the water in the pipette, hold it 5 centimeters above the penny, and slowly drop water onto the penny, 1 drop at a time. And you'll count the drops that you put on there. Line number 4. How many drops of water were on the penny before the water overflowed and went onto the tabletop? Record that here. And then repeat this 2 more times, so you have a total of 3 trials, 3 numbers of drops before it overflows onto the tabletop. And then you find the average. You find the average by adding these 3 numbers up and dividing by 3. Next, for 6 through 10, you're going to do the exact same thing, but instead of water, you're going to be using rubbing alcohol. Now, please remember, you don't need a lot of rubbing alcohol. Just a half an inch on the bottom of your beaker is going to be way more than necessary. Remember, you're just going to be piling this up on a penny, so you just need a little tiny bit. Question at the bottom. Compared to alcohol, how strong are the bonds that hold water molecules together? How do you come to that conclusion? So you're going to have to look at how big of a pile of these different liquids you can make, and from those sizes, determine how strongly the molecules pull on each other, holding each other in place. Activity number 2. We're comparing the densities of liquid water and solid water. Remember, density is how closely packed together the material is. And we're going to find out that ice is less dense than liquid water. Okay, activity number 2, water versus ice. Get 15 marshmallows and connect them on a paper towel with toothpicks in 3 rows. I'm sorry, that should not say toothpicks. That should say bamboo skewers. And it's going to end up looking sort of like this. So I have 5 marshmallows on each one of these skewers, and I put them close together like that. The next line, line number 2, place the 3 rows of marshmallows on a piece of graph paper, and they should be used as tightly as packed together as possible without smushing them. Have the marshmallow rows fit together like puzzle pieces, as I've shown here, where one marshmallow kind of fits in between the other 2. These marshmallows represent water molecules. They join in long strings, not as straight as this model, but close enough. And the long strings can flow past each other like slippery spaghetti noodles in a pot. That allows the water to flow. Number 3, draw a rectangle around the marshmallows and label it water in liquid phase. So I'm going to use a ruler here. And for my marshmallows, they go from one side all the way to the other, so I don't need to draw the ends of the rectangle. It's the edges of my paper. And then I'm going to find the area of that. Oh, I'm going to label it water in liquid phase. Then I'm going to find the area of that rectangle. So I'm going to use inches, just because I'm more comfortable with that. It's 11 inches long and 3 inches wide. So to find the area, you just multiply. For me, it's 11 by 3. You might get a different number. So I get an area of 33. Now, line number 6. Get 14 toothpicks and place them on a paper towel and make a model that looks like this. Have the same 1 inch toothpick showing. So we have 3 rings here. When water slows down, as it gets colder and colder, the molecules move around less and less, and they end up forming these rings with empty space on the inside. Here's my model of that. Your model might be a little bit different, but again, I'm going to make a rectangle around all of these marshmallows. It's going to be different than your earlier rectangle. And my rectangle is 10 inches, 10 inches long, and 7 inches high. So 10 left and right, 7 up and down. Figure out the area there. And we're going to label this. Let's see here. Oh, I didn't have the directions to label it. Let's label it as ice. Please label this graph ice. I guess it's not a graph, but a diagram. Okay, so number 8, lay this model on another graph paper, trace a rectangle around it, label this water in ice form. Up there I had it labeled. The rings are locked together, and they don't really break, so that's why ice is so strong. So find the area of that rectangle, we did that. Then answer these questions. Which takes up more space, 3 lengths of liquid water molecules or 3 ice rings? And we can see that the ice rings take up more space. If water entered cracks in a rock and froze, how might it affect the rock? Well, before, when we have liquid, the molecules can form nice, neat rows on the inside that lay very, very close together. You can get lots of water in that little crack. However, as the ice freezes, it expands to make these rings, and the expansion of the molecules can force the rock apart. Here, I'll zoom in a little bit so you can see a little more clearly how I have those drawn. There's the water molecules in nice rows, close together. That's before it freezes. And then after it freezes, we have the rings of ice, and the formation of those rings pushes the rock apart. That makes the rock into smaller pieces. Next pair of notes. Water expands as it freezes. Water expands as it freezes. As water freezes, its volume increases by about 10%, a little bit less than that. But this expansion is due to the empty space between the molecules. There's nothing between these molecules. It's not filled with air. It is like the emptiness of space. There are no other atoms in there. Because of these empty spaces, that is why ice floats. If water seeps into small areas within cracks and freezes, it will eventually break the rock into smaller pieces. This is called mechanical weathering. I'll read that one more time since it's kind of small on the screen. Let me zoom in a little bit more, I guess. Water expands as it freezes. As water freezes, its volume increases by 10% due to empty space between the molecules. This is why ice floats. If water seeps into small areas within rocks and freezes, it will eventually break the rock into smaller pieces. This is mechanical weathering. And I would like you to write down some more stuff in this blank area. I want you to write down that ice has a bigger volume pound for pound than water. So if you have 1 pound of water, and you freeze it to make 1 pound of ice, the ice will have a bigger volume. And then I want you to write down a very similar phrase. It's just written in the opposite sort of order. For each pound, water has a smaller volume than ice. You need to be able to know this in both directions. You don't know which form of the sentence is going to be on your quiz or test. Okay, that's the end of the notes. You do have a homework sheet that is attached to this. And to review very briefly for that review sheet, let's go over a couple diagrams. Remember that when you have rain, snow, sleet, all those kinds of things falling down, that is called precipitation. And precipitation, when it falls on land, if it flows over the surface of the land, we call that runoff. I guess I'll write precipitation over here. If the precipitation soaks down into the ground and gathers in the groundwater, we call that accumulation. Accumulation will also be if the water goes down into the ground and seeps down into a lake underground. Both of those underground things would be considered accumulation. Runoff is at the surface of the land. There are 3 different ways that water can end up in the atmosphere. It can go from the leaves of plants. It can go from the ground. It can also go from water. But in all of these cases, it's always called evaporation. That's when liquid water turns into water vapor. That can happen in leaves, and the dirt, and in open water. All 3 of those are evaporation. And then when the water vapor, the invisible water vapor that's in the air, moves and forms a cloud, it's forming little droplets. That forming of droplets is called condensation. So that's the water cycle, all of those arrows put together. Another thing that you need to know for your homework is these different areas of dirt. Here we have a lake, so all this water is seeping into the ground, and this area of the ground is going to be saturated with water because of the lake being at the same level. All the little tiny areas between dirt particles and sand particles are going to be soaked with water. And so we call that area the zone of saturation. Above this is an area where the dirt particles have air spaces between them. So we call that the zone of aeration. The boundary between these two is called the water table. Another thing you need to know for your homework are these graphs of the water table. The y-axis is the water table, in other words, how deep down the zone of saturation is, and then the x-axis is the month. January, February, March, April, May, June, July, etc. Now, when we have a flat line here, that means that the water table is not moving up or down. That means that the rain has to equal evaporation. As quickly as water evaporates from the ground, rain is replenishing it. Now, other things can happen as well. Rain soaks in as fast as it evaporates out and all this kind of stuff, but this is a simplified way of saying it. When the graph goes up, that means that the water table is getting closer and closer to zero depth. It's getting closer and closer to the surface, which is right up here at this level. Now that happens when there is more rain than evaporation. When you have lots of rain, Then the water table goes up higher and higher towards the surface. The ground is filling up with water, basically, just like the level of water in a jug goes up as you pour water into the jug. At the very top here, it meets the zero level. So that means that the water table is at the ground level. And the result of that would be a flood of some sort. There are other reasons for floods besides this water table rising, but we won't get into that right now. And then we have this part where the graph is going down. That means that the ground is getting more and more dry. The water level under the ground is getting farther and farther away from the surface. And so that happens when rain is less than evaporation. Again, that's slightly simplified, but that's the basic idea. The lack of rain makes the water table go down in an area. Okay, with that kind of review, you should be able to do the homework just fine. When you are done with these notes, show them to your teacher and he will mark them off. And when you finish the homework, show that as well, and your teacher will have the answer key. You can check off to see how well you did on the homework and just show that result to your teacher.